In this video we're going to be looking at hypothesis testing where there is an approximation required in calculating the probabilities. Now there are a couple of types of approximations. As you know, you can go from one discrete distribution to another, binomial to Poisson, or you could do either of those discrete distributions, binomial or Poisson, to normal distribution. We're going to look at both of these types in this video. So first type we're going to look at is the binomial to Poisson distribution. I'm going to start with a question. So it says a factory employs 550 workers. There is a virus in the surrounding area with a 1% chance of someone catching it. On one day, 13 workers were off sick with the virus. Is the likelihood of catching the virus higher at the factory? Test at 5% significance to find the critical region and judge whether the virus is more likely to occur in the factory workers. So as always with these, we have to define our random variable. So we're going to say x is the number of workers with the virus, and the distribution of x is that it has a binomial distribution of 550 and a probability p, which is what we will be testing. Our null hypothesis is that p is 1%, 0.01, and our alternative hypothesis is that the probability is greater than 0.01 because we're being asked to test whether the virus is more likely to occur. So that is seeing whether the probability is greater, and we're testing at the 5% significance level, so alpha is 0.05. So we're being asked to find the critical regions. So we're finding the probability that x is greater than or equal to the upper critical region, which is going to be less than or equal to our significance level. So we're going to be trying to find that. However, we're not going to be able to use our tables with this information here. So instead we're going to have to do an approximation. So we can say that x is approximately the same as y, where y has a Poisson distribution of 550 n times p. So y has a Poisson distribution of 5.5. And now we can use the tables in order to find that. So I want to find the two values that will give us a probability either side of 5%. So looking at the Poisson distribution tables where lambda is 5.5, the probability of y greater than or equal to 11 is 1 minus the probability of y less than or equal to 10, which gives us a probability of 0.0253. So that's obviously below the 5% significance level. The next one above that is the probability that y is greater than or equal to 12, which is 1 minus the probability of y less than or equal to 11, which gives us a probability of 0.0538. So we've demonstrated the two values either side of the significance level. This is the one that's below, so this is the one that we want to use. So the critical region is where x is greater than or equal to 11, and 13 is greater than or equal to 11. The reason I'm saying 13 is because we observed that 13 workers were off sick with the virus. So we can conclude then that the likelihood of catching the virus is higher at the factory. So in our conclusion we need to state that the context, the likelihood of catching the virus is higher at the factory, and we also need to state that we reject HO. Let's now move on to where we have to do a normal approximation. So going from a discrete distribution to a normal approximation. Let's read the question. Barclays Bank takes on 15 new female employees per week on average over the last 10 years. They have a new HR manager, over the next 4 weeks they employed 70 women. Has the rate at which they employ women changed? Test at 5% significance. So from this information, there's some key points to pick out. We've got a rate here, 15 female employees per week, and it says, has the rate at which they employ women changed? So it's not suggesting it's gone up or down, so it's suggesting that we've got to do a two-tailed test. So we'll define that when we write our alternative hypothesis. But first, we need to define our random variable. So we're going to say that x is the number of women employed per week, and the distribution of x is that it has a Poisson distribution of lambda, because we will be testing lambda. Our null hypothesis is that the rate stays at 15, and our alternative hypothesis is that lambda is not 15. And alpha here is 0.05. We have a 5% significance test. Because it's a two-tailed test, we're going to be splitting the significance value. So we need to state when we're going to reject HO. So we're going to reject the null hypothesis if the probability of x less than or equal to x is less than or equal to half of the significance level, 0.025, or we're going to reject HO if the probability of x greater than or equal to x is less than or equal to 0.025. Now we've got to do an approximation here, but before we do that, we're looking at a 4-week period. So x is for 1 week, so let's say that y is the number of women employed in 4 weeks. So we would say that y has a Poisson distribution of 60, and 60 isn't in our Poisson table, so we need to approximate y to another random variable, let's say q, and that's where q has a normal distribution with a mean of 60 and a variance of 60. Now our observed value is that 70 women were employed in a 4-week period. So we're finding the probability that y is greater than or equal to 70. We could also find the probability that y is less than or equal to 70, but because the mean is 60, we would expect less than or equal to 70 to be quite a high number. So there's no point in testing that, because there's no way that that is going to be less than 0.025. So as a general rule, really, when you've got a two-tail hypothesis test, you shouldn't really test both tails, because we know that this is going to be towards the upper tail of the information. So those are our two tails. The mean is obviously in the middle there. 70 is going to be more towards this side, so we're going to be testing the upper tail of the data. So we're not going to be using this one, because we will find that it's not less than or equal to 0.025. So looking at where y is greater than or equal to 70, if we're going to do that as a, say what q is equal to, q is greater than or equal to, well, we need to do a continuity correction. So the numbers either side of 70, we want 70, we want 71, we don't want 69. So the boundary there is 69.5. So now we need to standardize that. So that's the same as the probability that z is greater than or equal to 69.5 minus 60 over root 60. And this is the same as the probability that z is greater than or equal to 1.226. So drawing in my normal distribution, 1.226 we can say is about there, and we want this area. So we're going to be doing 1 minus the probability that z is less than or equal to 1.226. Now, because in our normal distribution tables we've got the probability of z less than or equal to 1.22 and the probability of z less than or equal to 1.23, this falls somewhat in the middle. So we could be more accurate by finding an average of these two probabilities and then doing 1 take away that. So that's exactly what we're going to do. So 1 minus these two probabilities added together and then divided by 2. So we're finding the average of those two results. So when we work that out, we're going to end up with a probability of 0.11025, and we can conclude then that 0.11025 is greater than 0.025, and so therefore the result is not significant. There has not been a change in the rate of women's employment, and so we accept our null hypothesis, HO. So we accept HO, we accept that that is still the rate at which women are employed at.